When implementing on and off delay relays with a three-phase magnetic starter and a stop/start station, separating the relay functions requires careful wiring using an auxiliary contact in the starter. Here's a step-by-step guide to properly wire the system. Firstly, connect the stop/start station to the coil of the magnetic starter. This ensures that the stop/start station directly controls the magnetic starter's engagement. Secondly, connect the auxiliary contact of the magnetic starter in parallel with the start button. This parallel connection is crucial for maintaining the starter's engagement even after the start button is released. Thirdly, connect the on-delay relay coil to the auxiliary contact in the 120 volts power supply. This wiring ensures that the on-delay relay is energized whenever the magnetic starter is engaged. Fourthly, connect the solenoid to the normally open contacts of the on-delay relay. This configuration means the solenoid will only be activated after the on-delay relay set time has elapsed. Fifthly, connect the off-delay relay coil to the stop button and the 120 volts power supply. This connection ensures the off-delay relay is energized the moment the stop button is pressed, initiating the off-delay sequence. Sixthly, connect the motor to the normally closed contacts of the off-delay relay. This configuration ensures the motor continues to run for the duration of the off-delay time after the stop button is pressed. Now, let's discuss the operation of this circuit. When the start button is pressed, the magnetic starter engages and the motor starts running. Simultaneously, the auxiliary contact closes, energizing the on-delay relay. After the on-delay time elapses, the on-delay relay's contacts close, activating the solenoid. When the stop button is pressed, the magnetic starter disengages and the motor stops running. The off-delay relay coil becomes energized, initiating its timing sequence. The solenoid closes immediately due to the broken circuit, and the motor continues to run for the duration of the off-delay time. Note that the on-delay and off-delay times will need to be adjusted to suit specific requirements. These adjustments are crucial for the proper sequencing and timing of the solenoid and motor operations. It might also be necessary to add a resistor in series with the solenoid to prevent it from drawing too much current. This is particularly important to protect the on-delay relay contacts and the solenoid itself. Regarding conductor sizing and overcurrent protection, several National Electrical Code, or NEC, articles are relevant. Article 430 covers motors, motor circuits, and controllers. Specifically, 430.22 addresses the ampacity of conductors. The conductors supplying a single motor used in a continuous duty application must have an ampacity of not less than 125% of the motor's full load current rating as determined by 430.6. For example, if a motor has a full load current rating of 10 amps, the conductors must be rated for at least 12.5 amps. Article 430.52 covers motor overcurrent protection. The type of overcurrent device used are such as inverse time circuit breakers or fuses affects the maximum allowable rating. For instance, inverse time circuit breakers can be rated up to 250% of the motor's full load current if needed for starting, while fuses are typically limited to a lower percentage. For control circuit conductors, Article 725 provides guidance. Specifically, 725.27 addresses the overcurrent protection for control circuits. The overcurrent protection should be sized appropriately based on the conductor ampacity and the type of control circuit. For Class 1 control circuits, the overcurrent protection must not exceed the ampacity of the control circuit conductors. For Class 2 and Class 3 control circuits, specific requirements apply based on the power source and circuit characteristics. Regarding the auxiliary contacts, ensure they are rated appropriately for the control voltage and current they will be switching. The contact rating should be sufficient to handle the inrush and steady-state current of the on-delay relay coil. Using underrated contacts can lead to premature failure and unreliable operation. For enclosures and mounting, ensure all components are housed in appropriate enclosures suitable for the environment. Motors and control equipment in industrial settings often require NEMA-rated enclosures to protect against dust, moisture, and other environmental factors. Man the components securely to prevent vibration and ensure reliable operation. For grounding and bonding, follow Article 250 of the NEC, which covers grounding and bonding requirements. All metal enclosures and non-current carrying metal parts must be properly grounded to provide a low impedance path for fault current. This is critical for safety and to prevent electrical shock hazards. Ensure the grounding conductors are sized appropriately based on the equipment grounding conductor requirements outlined in 250.122. When selecting the magnetic starter, consider the motor's horsepower and voltage ratings. The starter must be properly sized to handle the motor's full load current and inrush current during starting. Using an undersized starter can lead to overheating and premature failure. Also, ensure the starter's overload protection is properly set to protect the motor from overloads and prevent damage. For the on-delay and off-delay relays, select relays with appropriate time delay ranges and voltage ratings. The relay should be capable of providing the required delay times for the specific application. Adjustable time delay relays are often preferred, as they allow for fine-tuning the timing to optimize system performance. Also, ensure the relay contacts are rated appropriately for the voltage and current they will be switching. If the relays are switching inductive loads, such as solenoids, consider using relays with arc suppression features to minimize contact wear and extend relay life. Regarding the solenoid, select a solenoid that is compatible with the control voltage and has sufficient force to actuate the mechanical components it is intended to control. Consider the solenoid's duty cycle and ensure it is suitable for the intended application. For example, if the solenoid will be energized frequently, select the solenoid with a high duty cycle rating. If the solenoid will be exposed to harsh environmental conditions, select a solenoid with appropriate environmental protection. The control transformer selection is another important aspect. If the control circuit operates at a different voltage than the main power supply, a control transformer will be required to step down the voltage. The control transformer must be sized appropriately to handle the total volt-ampere load of all control circuit components, including the magnetic starter coil, on-delay relay coil, off-delay relay coil, and any other control devices. It is good practice to size the control transformer with some extra capacity to allow for future expansion or changes to the control circuit. In regards to the wiring methods, use appropriate wiring methods and materials for the specific application and environment. In industrial settings, it is common to use conduit and wire that is suitable for wet or damp locations. Ensure all wiring connections are secure and properly insulated. Use wire connectors that are listed and labeled for the specific type of wire being used. Follow all applicable codes and standards for wiring installations. When troubleshooting, use appropriate test equipment and procedures to diagnose problems. A multimeter can be used to check voltages, currents, and continuity. An insulation tester can be used to check the insulation resistance of conductors and equipment. Follow all safety precautions when working with electrical equipment and circuits. Always to energize circuits before working on them and use appropriate personal protective equipment such as gloves and safety glasses. Regarding the programmable logic controller, or PLC, integration in more advanced control systems, PLC may be used to implement the on-delay and off-delay functions. The PLC can provide more precise timing control and can be easily reconfigured to accommodate changes in the system requirements. When using a PLC, the magnetic starter coil, solenoid, and other control devices would be wired to the PLC output modules. The PLC input modules would be used to monitor the status of the start/stop station and other input signals. The PLC program would then be written to implement the desired control logic, including the on-delay and off-delay functions. With regards to energy efficiency considerations, optimize the control system for energy efficiency. Use energy-efficient motors and control devices. Minimize the on-delay and off-delay times to reduce energy consumption. Consider using variable frequency drives, or VFDs, to control the motor speed and reduce energy consumption during periods of light load. Also, implement a regular maintenance program to ensure all components are operating efficiently. When it comes to safety interlocks, incorporate safety interlocks into the control system to protect personnel and equipment. For example, a safety interlock can be used to prevent the motor from starting if a guard is not in place. Safety interlocks should be designed to be fail-safe, meaning that they will cause the system to shut down in the event of a failure. Regularly test and inspect safety interlocks to ensure they are functioning properly. Discussing surge protection. Protect the control system from voltage surges and transients. Voltage surges can damage sensitive electronic equipment such as PLC and relays. Surge protection devices, or SPDs, should be installed to divert surge current away from the equipment. SPD should be selected based on the voltage and current ratings of the system. When selecting components, consider the ambient temperature. Ensure all components are rated for the ambient temperature in which they will be installed. High ambient temperatures can reduce the lifespan of electronic components. If the ambient temperature is high, consider using components with high temperature ratings or providing additional cooling. Focusing on documentation, maintain accurate and up-to-date documentation for the control system. Documentation should include wiring diagrams, component specifications, and operating procedures. This documentation will be invaluable for troubleshooting and maintenance. Store the documentation in a safe and accessible location. When working with harmonics, address harmonic distortion in the electrical system. Nonlinear loads such as VFD can generate harmonic currents that can distort the voltage waveform and cause problems with other equipment. Harmonic filters can be used to reduce harmonic distortion. Perform a harmonic analysis of the electrical system to determine if harmonic filters are needed. Analyzing power factor correction. Improve the power factor of the electrical system. Low power factor can increase energy consumption and reduce the capacity of the electrical system. Power factor correction capacitors can be used to improve the power factor. Perform a power factor analysis of the electrical system to determine if power factor correction capacitors are needed. For remote monitoring, implement remote monitoring capabilities for the control system. Remote monitoring allows operators to monitor the status of the system from a remote location. This can be useful for identifying problems early and preventing downtime. Remote monitoring systems can also provide valuable data for analyzing system performance. Regarding preventative maintenance, establish a preventative maintenance program for the control system. Regularly inspect and test all components. Replace worn or damaged components. Keep the system clean and free of debris. A well-maintained system will operate more reliably and efficiently. In regards to training, provide adequate training for personnel who will be operating and maintaining the control system. Personnel should be trained on the proper operating procedures, troubleshooting techniques, and safety precautions. Regular training should be provided to keep personnel up to date on the latest technologies and best practices. If there are hazardous locations, ensure the control system is suitable for use in hazardous locations. Hazardous locations are areas where flammable gases, vapors, or dust may be present. Control systems used in hazardous locations must be designed to prevent ignition of these materials. Follow all applicable codes and standards for hazardous location installations. Considering load calculations, perform load calculations to ensure the electrical system has sufficient capacity to handle the control system load. The load calculation should include all control system components, as well as any other loads that are connected to the same electrical system. The electrical system should be designed to provide adequate power to all loads without overloading the system. When referring to the single-line diagrams, create single-line diagrams of the electrical system. Single-line diagrams provide a simplified representation of the electrical system, showing the major components and their interconnections. Single-line diagrams are useful for understanding the overall system configuration and for troubleshooting problems. Regarding coordination studies, perform coordination studies to ensure the overcurrent protection devices are properly coordinated. Coordination studies help to ensure that the overcurrent protection devices will trip in the correct sequence to minimize the extent of an outage. Coordination studies should be performed by a qualified electrical engineer. In regards to arc flash hazard analysis, perform an arc flash hazard analysis to determine the arc flash hazard levels at various points in the electrical system. The arc flash hazard analysis should be performed by a qualified electrical engineer. The results of the arc flash hazard analysis should be used to select appropriate personal protective equipment for personnel who will be working on the electrical system. For the NEC compliance, ensure the control system complies with all applicable requirements of the National Electrical Code, or NEC. The NEC provides comprehensive requirements for the safe installation and operation of electrical systems. It is important to consult the NEC and to follow all applicable requirements. Remember to use appropriately rated components. Always use components that are rated for the voltage, current, and environmental conditions in which they will be used. Using underrated components can lead to premature failure and create a safety hazard. If there is proper labeling, then label all components and wiring clearly. Clear labeling makes it easier to identify components and to troubleshoot problems. Use durable labels that will withstand the environmental conditions in which they will be installed. Ensure regular inspections. Regularly inspect the control system for signs of wear, damage, or corrosion. Replace worn or damaged components promptly. Keep the system clean and free of debris. A well-maintained system will operate more reliably and safely. And finally, regarding safety procedures, always follow safe electrical work practices. To energize circuits before working on them. Use appropriate personal protective equipment. Follow lockout/tagout procedures to prevent accidental energization. Be aware of the potential hazards and take steps to mitigate them. In summary, properly implementing and maintaining a control system involving magnetic starters, on and off delay relays, and auxiliary contacts requires careful attention to detail, adherence to safety standards, and a thorough understanding of electrical principles and the NEC.